Friends, very good morning to everyone. We were discussing with many reactions of aldehydes and ketones. If I oxidize the aldehydes, I'll get corresponding carboxylic acids very easily. Ketones are resistant to oxidation. Why is it so? It is attributed to the fact that it do not have a hydrogen attached to carbonyl group. But here is one reaction which is named after the scientists who invented this reaction, in which the ketones are oxidized to carboxylic esters. Yes, today's subject of discussion is Baeyer-Villiger oxidation. He is Victor Villiger, a Swiss-born German chemist, and is the discoverer of Baeyer-Villiger oxidation. He studied at University of Geneva, followed by his doctoral studies with Adolf von Baeyer at University of Munich. The teacher and the student together they invented this reaction, and that's why it's named after them as Baeyer-Villiger oxidation. He is Adolf von Baeyer. Adolf von Baeyer is also a German chemist, and he synthesized indigo for the first time and also developed the nomenclature for cyclic compounds. He proposed the Baeyer strain theory to explain the stability of cycloalkanes in 1885. He has been the recipient of Nobel Prize in Chemistry in the year 1905. Let us look into this Baeyer-Villiger oxidation. Baeyer-Villiger oxidation is a reaction in which the ketones gets oxidized to carboxylic acids by using a peroxy acid as an oxidizing agent. In Baeyer-Villiger oxidation, the ketone oxidizes to carboxylic acid ester, and the peroxy acid which we used, it gets reduced to carboxylic acid. Here, if I take a ketone R1COR2 and treat with peroxy acid or peroxide, I'll get R1COOR2, an ester. If I take cyclic ketones instead of the aliphatic ketones, when I treat with peroxy acid or peroxide, it gets converted into lactone with one carbon extra than the original ketone. This is the salient feature of this Baeyer-Villiger oxidation. Similarly, if I take cyclopentanone and treat with peracetic acid in the presence of chloroform as the solvent, I'll get tetrahydroperone 2-one. Is also having one carbon extra than the original, and a lactone is formed. If I take 2-methyl cyclohexanone and treat with a peracid, I'll get 7-methyl oxapen 2-one. Here, how this reaction occurs? What's the mechanism behind it? Let us look into it. The peroxy acid which is used is generally spelled as peracid also. Carboxylic acid is represented as COOH. Here, this has carboxylic acid has one OH group. Here it has, instead of OH group, this has OOH group. That are peracids. If I take a ketone and acetone, we take as a representative of ketone and treat with a per acid or C double bond O OOH. This has the lone pair of electrons, and the lone pair of electrons gets protonated. The protonation of the oxygen takes place. The per acid acts as an acid donor. It donates H plus, and electrons from the oxygen combines with this hydrogen, and the electrons are shared with OH, and hence the protonation of the carbonyl oxygen took place. This is the first step in the reaction process. As the electrons are shared with hydrogen and oxygen has to be divalent, but now it has become trivalent, hence it has become positive. It has become electron deficient. To satisfy this positive center, the pi electrons moves towards the oxygen. Once this electrons moves towards oxygen, it renders the carbon attached to this oxygen much more positive. In turn, it has increased the positivity or electron deficiency of the carbon. This is electron deficient carbonyl carbon, and this is electron rich anion. This oxygen anion combines with the carbonyl carbon, and an intermediate of this sort is formed. Here the nucleophilic attack has taken place, and it is unstable. The electrons on the oxygen moves back towards the carbon. It forms double bond, and the carbon and carbon bond breaks. The electrons are taken by methyl, and methyl along with its electron pair moves towards the oxygen, and the RCOO group gets kicked off. Here 1, 2 alkyl shift has occurred towards electron deficient oxygen. Now I have got a protonated ester and a carboxylate anion. In the presence of a base, the proton get abstracted, and as it is positive, the electrons moves towards the oxygen to satisfy the positive center, and the H plus combines with the B and forms BH, and it gives corresponding ethyl ester and a carboxylate ion. This is Baeyer-Villiger oxidation. The ketones are generally not oxidizable. They are resistant to oxidation. Even if we oxidize, it breaks the molecule and gives the smaller products. Thus, this is a method developed by Baeyer and Villiger where we get corresponding esters. Hence, this is a good contribution from these two scientists. In memory of them, to recognize the contribution, this reaction is named after them as Baeyer-Villiger oxidation. Next class, we can deal with other reactions. Till then, have a nice day. Thank you.